the infrared region and the analysis of compounds when they are bombarded with electromagnetic radiation of these wavelengths which fall in infrared region, they bring about some changes in the compounds. That changes in the compounds also affect the radiations falling on them. The changes, the compounds, they absorb the infrared radiation which is suitable. Okay, suitable for suitable for that compound. It does not mean that all the infrared radiation will be absorbed by all the compounds. They absorb those radiation depending on their characteristic. The infrared region of the spectrum encompasses the radiation wave numbers ranging from 12,800 centimeter inverse to 10 centimeter inverse. This is in terms of wave numbers. If you want to talk about wavelengths, the wavelength ranges from 0.78 to 1000 micrometer. The infrared spectrum is divided into three parts: near infrared, mid infrared, and far infrared radiation regions. Now, depending on three ranges, we can say that near infrared is between wavelength of 0.78 micrometer to 2.5 micrometer. In terms of wave number, it is 12,800 to 4,000 centimeter inverse. Please note that when we talk about wavelength, we start from smaller number to larger wave number, and for wave numbers, we start from larger to lower wave number. The middle region of infrared spectrum ranges from 2.5 micrometer to 50 micrometer or 4,000 centimeter inverse to 200 centimeter inverse. In case of far infrared region, it is from 50 micrometer to 1000 micrometer. In terms of wave number, it is 200 to 10 centimeter inverse. Now, most used part of the infrared region is 2.5 to 15. It falls somewhere here in the mid infrared region. Same, if you will see that 4000 to 670, that means it falls in this wave number region. Now, so most of the analysis which is relevant to organic chemist, the pharmaceutical chemist, is falling in mid infrared region. Okay. Uh, if we also have some application, we also have some application in near IR region. We will see that later, but most used part in, you can say, the specialized IR spectroscopy is the mid IR. I have purposely avoided mentioning of frequency to avoid confusion. Okay, let's dive into the theory of infrared spectroscopy. If you will see the infrared spectrum on x-axis, you will observe that it is wave number. It ranges from 4000 to 650. Now you must have got the idea why we are starting with larger number and ending up in lower number in case of wave number. Now, there is one additional x-axis to this IR spectra, which is a little bit unusual for in general spectroscopy. Okay, upper x-axis you have wavelength. It ranges from 2.5 micrometer to say 16 micrometer. Okay, now on y-axis you have transmittance or percent transmittance. Okay, generally percent transmittance term is preferred. So highest transmittance will be 100 and the lowest transmittance is 0. When transmittance is 0, it means absorbance is very high. When transmittance is 100, it means absorbance is very low. Now, this is how IR spectra looks like. Let's read into it. What is this? Is the just the explanation of that appearance of the spectra. The ordinance is uh, the ordinance is linear in transmittance. Ordinance is your y-axis. The abscissa is linear in wave numbers. Abscissa means the x-axis. X-axis have wave numbers with units reciprocal centimeter, that is centimeter inverse. Modern instruments utilize microcomputer capable of producing a variety of other formats of output, such as transmittance versus wavelength, absorbance versus wavelength, or wave number. So basically, different forms of expressing the wave number and wavelengths can be on x-axis, and different forms of transmittance can be on y-axis. So the previous two slides were talking about how the IR spectra appears. Now let us see what is the root cause of obtaining that spectra in that wavelength range, in that wave number range. Now when you imagine any molecule, you can imagine the molecule as every atom nucleus is representing one ball, and the bond between them is like a spring. So any molecule will be in constant mode of vibration. Constantly it will be vibrating. When we say vibration, the vibrations can be of multiple types. Like there may be change in the bond length frequently. Okay, like bond length shrinking and expanding. There may be change in bond angle. There may be twisting of the bonds, and so on. So there are lots of changing occurring within the molecule without breaking the bond. Now, when these changes occur within the molecule, the atoms are getting closer and away from each other repetitively. These atoms, when they have different electronegativity, they have different density of electron clouds around them. I repeat, if the atoms which are forming the molecule have different electronegativity, so maybe one atom within the molecule has more electron density around it as compared to other atom. So overall takes a form of dipole. The molecule takes the form of dipole, and these dipole are vibrating. These were dipoles are vibrating. When we originally talk about the difference in the electron density and their movement, which are coming closer and going away, so that electric field will be associated with the magnetic field also. So the magnetic field around the molecule is also changing in a systematic manner, like a vibration. It is diminishing and it is increasing. So there are dipole changes as if they are vibration associated with the molecule. So dipole changes during the vibrations. Infrared radiation is not energetic enough to bring about electronic transition as compared to UV. Like pi electrons of the molecules cannot jump to anti-bonding pi star. Sigma electrons cannot jump into anti-bonding sigma star. So electronic transitions are not possible because infrared radiations are weaker radiations. Absorption of infrared radiation is thus confined largely to molecular species that have small energy differences between various vibrational and rotational states. So when infrared ray energy is absorbed by molecule, what is being changed within the molecule? Only they will either start vibrating more or they will start rotating more. So this is the way they are absorbing the energy. I repeat, the molecule cannot undergo electronic transitions. The electrons remain in their shells and subshells of the molecular organism. What changes is the way molecules vibrate and rotate. In order to absorb infrared radiation, a molecule must undergo a net change in dipole moment as a consequence of its vibrational or rotational motion. That means if a molecule is not vibrating, if molecule is not vibrating, which is associated with the dipole moment, there will be no changes, no vibration in the dipole moment. If there is no net change in the dipole moment, the molecule cannot absorb infrared radiation. So I will give you two examples of molecule. One molecule is, say, HCl. The other molecule is Cl2. So out of these two molecules, observe them carefully. Which molecule has dipole within it? I need to. I need your answer in the chat box or unmute and tell me. The
First
two
one, HCl.
Excellent, excellent. So HCl will be associated with the dipole moment. In case of HCl, there is dipole moment associated with it. In case of Cl2, because there is no electronegativity difference between two atoms forming the molecules, there is no distribution of charges, so no dipole moment associated with the molecule. So out of HCl and Cl2, only HCl will express, HCl will be associated with changes, net changes in the dipole moment. So HCl can absorb infrared radiation, but Cl2 cannot absorb infrared radiation. Dipole moment is determined by the magnitude of the charge difference. Magnitude of the charge difference. The distance between two centers of the charge. You must have remember the formula, that is charge on one atom multiplied by charge on second atom divided by the square of distance between them. Okay, so the distance and magnitude of the charges is important. Okay, both of it is important. It determines how large or small the dipole moment is. No net rotation of homonuclear species because the charge on both of them is same. So there is no net charge difference like O2, N2, Cl2. Consequently, such compound cannot absorb infrared radiation. Now, let's go on a little deep, explore more vibrations. Now, there is a concept called as vibrational transitions. We have seen what is electronic transitions. There is also something called as vibrational transitions. Any guess what must be happening in vibrational transitions? Okay, what happens in electronic transition? The energy of the electrons changes. So in case of vibrational transition, what it must be? Meg, it is not actually the electrons themselves, they are absorbing the energy. What about wavelength, Shubham? Wavelength changes. Wavelength will not change. The wavelength will remain same for that electromagnetic radiation falling on the molecule. See, what happens is initially molecule is in one vibrational state. After absorbing the energy, that energy will be absorbed by the molecule and it will go to higher energy level only by vibrating more. Yes, Pooja Jaiswal. It occurs between different vibrational states. Very good. Pooja is absolutely right. So instead of changing the electronic state, we are changing the vibrational state. Okay. Vibration energy levels are quantized. Vibrational energy levels are quantized, and for most molecules, the energy differences between the quantum states compounds correspond to mid-infrared region. Now, many of you may not have understood this statement. Let me open a whiteboard. I will tell you what it means. Suppose this is the ground state of a molecule. Okay. Nominal vibration of the molecule when at room temperature molecule is vibrating at this particular state. Now, this is say dipole, two different atoms attached to each other via a bond. Now, as you must have heard, for a thread, there is different modes of vibration. There is fundamental mode of vibration. Then there is, for a thread, there is first mode of vibration. Then there is second mode of vibration where there are two nodes. Okay, this is 0 node, this is 1 node, this is 2 nodes. So this is fundamental mode of vibration. This is first mode of vibration. This is second mode of vibration. It has got the least energy. And energy is more in case of first mode. Energy is furthermore in second mode of vibration. So this was related to a string attached to two fixed support. Same thing can be said about the bond attaching two atoms. Okay, this bond is also vibrating. It is changing its length, bond length. So at ground state, this is the fundamental mode of vibration. It may absorb certain energy and jump to say next mode of vibration. It may absorb certain more energy to go into third mode of vibration. Okay. Now, have you understood this? There is different modes of vibration. Have you understood so far? Okay, few students are saying yes, they have understood. Okay, good. So what happens is, for one particular molecule, oh, that screen just went away when I changed the slide. Okay, for certain molecule, see, every molecule is unique. Every molecule is unique. So the energy difference between V1 and V0 and V2 and V0 and between V2 and V1 is different for every molecule, and it is characteristic of that molecule. I should say furthermore, it will be characteristic of that particular bond. Like for HO bond, it will be different. For HC bond, it will be different. For CH bond, it will be different. All the fundamental first and second mode of vibration, modes of vibration will be different for different types of bonds. Okay, I hope you understood so much so far. Okay, I will escape this white screen. So, if you have understood that much, I will read out the part which is written here. It will be more relevant to you right after I read it now. Vibrational energy levels are quantized. That means the energy difference between them is fixed. Discrete. The energy difference between two levels of vibration is discrete. For most molecules, the energy differences between quantum states correspond to mid-infrared region. The energy difference between two levels, if you translate that into wavelength, that wavelength will fall in mid-infrared region. Now, moving forward, Now we understand that there are different vibrational transitions. So vibrational transitions, if they are different, there will be different vibrations also. So let's see what is different types of molecular vibrations. Now, different types of molecular vibration and different modes of molecular vibration, they are different. Modes of vibration is different and types of molecular vibration is different. Take a note of that. We will see what is different modes of vibration also. For time being, we are looking at types of molecular vibration. Vibrations falls into the basic categories of stretching and bending. A stretching vibration involves a continuous change in the interatomic distance, also called as bond length, along the axis of the bond between two atoms. So in stretching vibration, the distance between two atoms changes. Atoms come closer and go farther from each other. Bending vibrations are characterized by a change in the angle between two atoms and of four types: scissoring, rocking, wagging, and twisting. Let us see what all those are. First two are stretching vibrations. This is one atom. This atom is connected to two different atoms. These two atoms may be same, they may be different. Okay. Now, when the atoms attached to the central atom go away from it together simultaneously, it is called as symmetric. In asymmetric stretching, as one atom goes away from the central atom, the other atom comes nearer to it. And vice versa, when it is moving away, this atom will come closer. So, this molecule here is performing stretching vibrations in a symmetric manner, and over here this molecule is performing stretching vibrations in symmetric manner. Okay. Now, when we talk about bending vibrations, they are of two types: in plane and out of plane. When we say in plane, all three atoms involved throughout the vibration, they remain on the same plane. In case of out of plane vibration, bending vibrations, the three atoms involved, they do not remain in the same plane. They change their plane. Let us see what is in plane vibrations. In plane vibrations are of two types: rocking and scissoring. In case of rocking, both the atoms, they start moving towards the same side. They start moving towards the same side, and relatively the central atoms remain stationary. I am saying relatively, it is not absolutely stationary. Okay, so this is called as rocking in plane bending vibration. Okay, it is type of bending vibration. It is called as in plane rocking. There is another vibration where central atom is relatively stationary and both the atoms connected to it, they move closer to each other and then away from each other. So this type of bending vibration is analogous to movement of scissors. Both the blades of scissors, they come closer and they move away from it. But in both these type of vibration, all three atoms, they remain in the same plane. So it is in plane scissoring bending vibration. Now, next type of vibration is out of plane vibration. That means this central atom is relatively stationary. These two atoms are together coming out of the plane and going behind the plane. Coming out of the plane and going behind the plane, and their relative position to each other is remaining in one plane. So if I have to name the atoms, suppose this is atom A, this is atom B, and atom C. So atom A and C will be always in same plane. either coming out of the plane towards the observer or going behind the plane away from the observer. While the movement of B is exactly opposite. When A and C are coming out of the plane, atom B is going moving behind the plane and vice versa. Now, I want you people to note that there is plus sign and there is minus sign over here. Plus sign indicates that those atoms are moving towards the observer, and minus sign indicates the atom is moving away from the observer behind the plane. Now, coming to the last type of vibration, here you will see there is plus sign over here, there is minus sign over here, and there is no any sign on the middle atom. It means this atom all the time remains on the plane of the paper or plane of the screen, while one atom's coming out of the plane, the other atom is going behind the plane. This type of movement is like twisting, so it is called as out of plane twisting. It is also type of bending vibration. So that was the theory behind IR spectra. Okay. Now the theory so far explains different levels of vibration. As the vibrations are occurring, there is change in dipole moment, and when there is change in dipole moment, when dipole associated with the molecule is vibrating, it may absorb electromagnetic radiation of corresponding energy. Okay, this much we have understood. So let us try to relate what we have studied so far with the molecular spectra that we observe. There are three basic types of optical spectra that we can observe for molecules. We have seen the first type of spectra already, the UV spectra. Okay, what happens in UV spectra can be understood by this diagram on your right hand side. I will zoom into the diagram. See, there are different levels of molecular orbitals. When that molecule absorbs energy, the energy is absorbed by the electrons themselves, which are in different molecular orbitals. These lines are representing different molecular orbitals, and their level indicates the energy. Like here, the second orbital, molecular orbital, is at higher electronic state as compared to this one, and this is at higher energy state as this one. Now focus on the longer lines only. Okay, so when the energy is sufficient enough, the electrons jump from lower energy level to higher energy level. See, these 0, 1, 2 are corresponding high energy levels. Okay, so what you can see here is longer lines, and you can see those smaller lines. Okay, now what those lines represent is vibrational and rotational levels. Vibrational and rotation levels of molecular electronic states are A and B. Okay, so these are molecular vibration, and these small lines are rotational vibrations. This large line is again indicating the vibrational state, and smaller line the rotational state. The vibrational levels are given by V double dash and V dash. You can see that on right hand side, V dash and V double dash. While the rotational levels are given by J double dash and J dash. So we can see that these different are rotational levels J dash, and these are different rotational levels at V double dash indicated by J double dash. Okay, the three arrows show the three types of transitions possible, that is X, Y, and Z. So this one is X, which is the longest one associated with the highest energy level. This is the Y one, and this is the Z one. So let us see what are those X, Y, and Z. Electronic and vibronic spectra. It is UV visible near IR spectra. Transitions between a specific vibrational and rotational level of one electronic state and a vibrational and a rotational level of another electronic state. So this is one electronic state, this is another electronic state. Okay, we are at zero level of vibration and at say third level of rotational. Okay, so over here is the energy of molecule. From this, energy is absorbed and it jumps to over here, which is the second level of vibration and second level of translational. So what all things are happening? It is between specific vibration and rotation. This part is referring to over here, and jump has to a different electronic state and vibrational state over here. Okay, so this is the transition. Now, moving further, vibrational and vibrational rotational spectra. Transition from rotation levels of one vibrational level. So, this is one rotational level of this vibrational state to the rotation levels of another vibration level in the same electronic state. So electronic state is remaining same, but what is being changed? We are getting change in vibrational level. See, we are at different vibrational level and at different rotational level. Here it was at this say third line, here it is at fourth line. So even the rotational level is different, vibrational level is different. Okay, so it is given by Y. The previous one was given by X. X is electronic, Y is vibrational and rotational. Third is rotational spectra. It falls in microwave region. It is transition between rotation levels of the same vibration level of the same electronic state. So it is occurring within the electronic state, within the vibrational level. If you can observe that small z over here. So it is only change in rotation. We will stop here today, and I want you people to give your attendance as per your new roll numbers.